Okay, welcome. Welcome back, everybody. Okay, welcome everybody to the second lecture of the second week of the module on knowledge, and particular knowledge for intelligent agent and knowledge for games. Just a quick question, show of hands. I published yesterday the videos of yesterday's lecture, and I wasn't sure whether I should put an announcement that I've done so. So who would prefer me sending quick announcements if I put some information here? Can you please raise a hand then? And who would prefer not to get that many announcements? Sorry guys, I'll spam. I'll try to keep it in sort of in the middle, not too often, but when there's some information, maybe gather it and then put it online. So the videos are online, as I just said, so that you can watch what I explained yesterday. And today I want to spend on giving a bit more information about first order logic, because that was rather quick yesterday. Again, sort of more reminding you of what you've seen before. Yes?
Do you think you need to rewatch the lecture from yesterday if you watched the lecture from last year? Would you recommend that?
No. I have to think a bit. So I would watch the first half. If you can't remember exactly what we did, or if you haven't been here yesterday, so the first half where we went through the two games, the Wumpus World, and thought of them in terms of a game tree.
Yeah, that was the same as last year.
No, that was different. So the particular the Schnapsen one, I didn't do last year. So thinking about the different rules and strategies in the game in terms of logical formulae, we didn't do last year. And I think I liked that part yesterday. So I thought that was very interesting when you're coming up with all these different strategies. And I'm not sure how easy it is to listen, to hear what you said, but it might be useful still. So as I said, I want to sort of continue the reminder on first order logic to start with, and then give you some examples of how to make decisions with logic. In particular, how to represent games in first order logic, because it's a more elegant way of dealing with this kind of information. And then, as I want to show you tomorrow, a reasoner, an automatic reasoning tool in propositional logic, I also want you to see how you can formulate your knowledge that you have modeled in first order logic, how you can translate that into propositional logic, and a little bit the interrelation between the two. And at the end, I want to have a brief discussion or give you my vision on the final project. So that's the plan for today. And as I said yesterday, I sort of, although it is meant as a reminder, so for you to get up to your head the ideas that you've looked into last year in the logic and sets course, or so if you really want to go in depth, you have to you should read the reader, for example. I added the chapter on first order logic from the book also as a reader on one of the pages where to get started. I think it's very useful to read those chapters in addition to what I explain here. There is more material. Not all the material comes in the exam, but it's relevant for you, or it can be interesting to broaden your horizon. So yesterday was only meant to remind you of the logic of formalisms, but it was still very short at the end, what I said about first order logic, in particular about the quantifiers. And I want to talk a little bit more about the quantifiers before getting into the game itself. So the way you construct your sentences in first order logic containing quantifiers is that you start with either the existential quantifier or in this case the universal quantifier, and these are the two symbols that I hope you're familiar with. And then you have a set or a chain or a number of variables that you quantify over, and a sentence which can be complex, containing disjunction, predicates, functions, and so forth, but also the variables over which you quantify. So here we have only one variable, but there could be more, and you have a complex sentence which is from here to here with quantification over the variable x and a constant US government in this case, and a predicate smart. And the meaning is, of course, in whatever way you interpret x in your discourse of universe of discourse, if things are in this relation, the x relation, in an at relation between the x and the constant US government, then the x must also be smart, so the predicate smart of x must also hold. And semantically, this means that for all x p is true in a model, if p is true with x being each possible object in the model, just as I said. Just take any interpretation of x with an object from your interpretation and then check whether this p holds for this specific interpretation. And something we will need later is that you can translate that basically into a conjunction of instantiations of p. So if we know that our domain of discourse is finite and we know which are the objects in it, then we can just apply this conjunction over all these implications with grounded terms, as it's called, so where we replace the variables with one of these objects. And we do that systematically, and then we get a logically equivalent formula in propositional logic now. So if we have this formula for all x, US gov implies smart of x, and we know which x to apply it to, namely to King John, US government, and Richard, then we can simply state all the possible combinations of propositionalized formula. And that also gives you an idea of what the intended meaning is. And we do the same for the existential quantification. Again, the syntax is that we start with a list of variables, and then a sentence to which we apply these variables, they quantify over. Here we have the example that there is something, some object x in my domain, and it is in an at relation to the object US government, and now that's important that you use the quantifier and here, that specific object is also smart, so the smart of x holds. And the meaning, the intended meaning here is that there exists an xp is true if, in a specific model, if p is true with x being some possible object in the model. So you just choose one object in the domain and you check whether the property p holds. And it's obviously now different to the one we had before. Here we had a conjunction of implication, and here we have a disjunction of instantiations. So we now have the same systematic instantiation of all the objects, but now we have a disjunction. So it is either the interpretation that King John would be x and King John is smart, or it is Richard who is smart, or it could also be the thing, the object, US government itself. So we have to do it over all possible objects in the domain. So let's remind us of some of the properties of these quantifiers, and that is basically that they are, the order doesn't matter in this case. So if we have for all x, for all y, then this is the same as for all y, for all x, and we usually write down for all x, comma y to abbreviate this. But it's not the same when the quantifiers are mixed. So if there exists one for which all x p must hold, for example, then that doesn't mean that for all of them there exists one where x holds. And the example here is if you have a love x-y relation and you have the quantifiers x, there exists an x for all y, then this means that there is a person who loves everyone in the world. And if you turn around the order of the quantifiers, if you say for all y there exists an x, loves x, y, then everyone in the world is loved by at least one person. And I think you can intuitively understand that these are two different things. They represent two different kinds of information. One thing that's mostly technical, and that's something that you will need later in the rewriting when we do some reasoning over these logics, is that you can write the one operator in terms of the other. So here's the example that if you say for all x likes x ice cream, so that means everybody likes ice cream, then that is the same as to say there does not exist anybody who does not like ice cream. You think about it, and that is the way to write it down here, so that it does not exist someone who does not like ice cream. And there is the duality of the quantifiers. Instead of writing for all x, p, we can always write non exists non-p of x. Yeah? Okay. And there are obviously many very useful examples of how to use first-order logic. First-order logic has been around for now 130 years, I think, as a formalism, and has been one of the main targets for automation. Since the past 60, 70 years, people have tried to automate the reasoning processes in logics, and first-order logic has really drawn most of the attention. And there are nice and interesting examples for usage, in particular in mathematical theorem proving. That's where this was also originally started with. But there is a big problem, and that is computational properties of this logic, to which I will get in a minute. I would just focus here now for a minute in the examples from our gaming world, from the Wampus world, but this is far more than just a toy language. You know? But what you can state things like whenever someone is a brother, so x and y are in a brother relation, then x and y must also be in a sibling relation. So basically stating that brother relation is more general than, is more specific than the sibling relation. So now you define properties between what does it mean for someone to be a brother and what does it mean for someone to be a sibling. But you can say far more complex things. So one's mother is one's female parent. So if C is a mother in a mother relation, and then we know that she must be female and that she must be in a parent relation to the object C, if I talk about the person C here. We can also say more. We can define specific properties of the relations that we have. So in this case, sibling, we want to say that sibling, one of the important properties of sibling is that it's symmetric. So that whenever I'm in a sibling relation with someone, then this person is also in a sibling relation with myself. So my sister is in a sibling relation with me, but that also means that I'm in a sibling relation with my sister. And this statement is so generic that it now says something about the sibling relation and not about me. So it basically defines symmetry of the sibling relation. And in first-order logic, you can define many of the important properties of relations in this way. So you can define transitivity, you can define reflexivity, and so forth. There are some relations that you cannot define. There you need higher order logic for, but with first-order logic, you can already say a lot of these things. So before we move to some examples in our gaming world, just some warning on typical mistakes that you have to avoid. And as I showed you, the standard way of doing things is that you say for all x, p of x implies q of x. And sometimes it happens that people do not do an implication relation, but a conjunction relation. And that basically has a very different semantics, or a very different meaning. And you have to be careful, because if you write down for all x, AT x of US government and smart of x, then what you basically say is that everyone is at the US government, full stop, and also everybody is smart. And that is a completely different thing to say, because the intended statement you wanted to make is that if you work for the US government, then you'll be smart, so you need the implication in this formula. And this completely ruins what you wanted to say. So it's a very different thing to say. The problem why you would say that is because if you have an existential quantified statement, this is usually what you want to say in a conjunctive form. So you usually want to say there exists something with two properties, namely the property being of the United Government and the property of being smart. And those two predicates must then hold for both of those, have both to hold for x. So if you write down your statement that there is someone in the intended statement that there's someone in the US government who's smart, and you write it down like this, then you get a completely different meaning again, because now if someone is there who's not in the US government, so for which the first statement does not hold, then the fallacy of logic, where you say if something is false, everything is implied, makes sure that in that case, everybody who does not work for the US government is suddenly smart. So if you find someone, I have to say not everybody, but if you find someone who is not in the US government, for which this is false, you can conclude that this person must be smart, which is again not what you wanted to say. So these are two modeling fallacies or problems that you often encounter when people work with first order logic. And finally, to give you some examples of what you would like to use if you model information about the Wampus world. So if you want to implement a logical agent who helps you maneuver around the Wampus gaming world, then this is the kind of information you would like to bring out. In particular, when you want to have more operators such as Thronier, or what is it, the arrow, shooting an arrow, and all these kind of stuff. So here you can now model the things about the perception, but also about the rules that you apply, about the reflexes that your agent should have. So the second one is, for example, so if you are in a situation where you perceive some glitter, where you have to define first what it means for something to be perceived as glitter. But if you are in this situation, then the best action you can have is to grab that thing. Yeah? In order to be able to use it. So this kind of attribute, best action, is also something that we obviously want if we want to define our strategies in Schnapsen later. We want to, the best strategy can differ for different persons, for different situations, but we can define them in this kind of way. And this one is a very simple reflex rule, a reflex agent, very simple. It takes some observation and it performs an action. What we need to do is here to define what it means for something to be a glitter, and that is basically, if we have a perception action, then we assign, and we have in this that one of the percepts is that there is a glitter, then we can define that this object T is a glitters, or this position we are in. We can obviously also define more complex kinds of rules, so not only the reflex ones, but also ones where we have a representation of the state, like I explained on Friday. So if you have an explicit representation of the state, which strategy to apply, for example, that you don't immediately, that you have more checks, not only check your rules on the basis of some perceptions, but also if you are in the third phase of the game, in Schnapsen, for example, after 3 tricks, you want to maybe apply a different strategy. And that is something that you could write down here. In which state of the game am I? How many tricks have already been played? Or what other cards do I have in my hand? So this is a very simple example for a rule, but obviously a more intelligent, a more rational agent also wants to represent a state or wants to represent some learned experience and so forth. You can also define some properties about the game engine, the game states themselves, because you remember that we had this tedious thing of defining that there had to be a breeze in another state or a pit in another state if we perceived a breeze. And then we had first to define, to which does this apply, and then all the adjacent ones. But we didn't have an explicit notion of adjacency. And in first order logic, you can define that in a very elegant way. You can just say 2 points x, y, and a, b in my grid are adjacent if a, b is in this set. So either you go 1 up and remain on the same level, or you go 1 down and you remain the same level, or you go 1 to the right, or you go 1 to the left. And these are the 4 possibilities of being in an adjacent state, up, down, left, and right. And if AB is in this set of possible states, then these 2 points, these 2 fields we are in are adjacent. So that's a generic definition of a property that I can now use in the definition of my strategies, for example. So if in all the adjacent fields, there is no stinch, then I can move to any of the adjacent fields. These kind of rules I can now state because I have sort of defined those properties. And I can now do reasoning on this kind of abstraction level, definition level of, as I can show here. So if I have more properties, so if an agent is at a position and there is a breeze t, breezy, then we assign, if the agent perceives a breeze, then it gives a property of a square to be breezy. So that's in a way it is a transition between the perception of the agent and some quality of the state. And then we can, for example, try to find out here and model the information of being breezy is the same or must imply that there exists an existent state where there is a pit. So that's the game information that we had modeled in propositional logic implicitly by, if you remember, if we had this somewhere, this square, and we had this breezy, then we had to add the information that either that is a pit, or that is a pit, or that is a pit, or that is a pit. Yeah? And here we can just write down that thing in one line by saying, if something is an adjacent field, and I have a breeze, then I can, if it's breezy, if I'm in this situation, then everything that's an adjacent field must have a pit. And it must be an existential quantified. So there must be somewhere a field adjacent that contains a pit. This is the information that I need. That's also all the information that I need in order to do some more reasoning later, in order to define a state that is safe and so forth. Oops. And I can do this in two directions. I can say that if something is breezy, then there must be an adjacent pit. That's the first statement. Or the other one, if there is a pit, then there must be an adjacent state where it's breezy. Yeah?
Sorry, what does the dollar sign stand for? It R and then there is a dollar sign?
I think that is a typo, probably. I don't think it has a meaning, so I will have to check it, but I think that sort of looks better. So as you can see, with this language, we can very elegantly describe a lot of the properties of the game, and not only the state itself, but also the rules in the first place, and the combination, the information that the agent gets from the sensors, and turn it into qualitative information to which it can then reason over, and in the end make the decisions, write the rules that you want to apply. So how does it work? Are we going to do this gameplay in our intelligent agent? You remember what I said about the problems that we have with Schnapsen in the first phase, that we have the uncertainty about the cards in the pile, and we have the uncertainty about the cards in the opponent's hand, which means that we do not know what the possible belief states, what the possible decks of cards of my opponents are, which means that I have to somehow reason over the belief states, and that there are so many that I can't completely reason over them. And the one method is to do sampling on those, but the other method is to sort of define a human strategy. And that's what we, I think, did very nicely yesterday in the first half, to look at a specific state and saw three different, very valid strategies to play. And now the question is, how can we model different of those strategies and maybe combine them and have our intelligent agents play while play in an intelligent way where the strategies have been modeled by humans. And then the research project later will be to evaluate which of those strategies is useful and which one is not, or good or not so good. But the technology that we want to use is to model in some kind of logic and then do some automatic reasoning over this logical knowledge base. And basically the outcome of the reasoning will give us the best strategy, or the strategy that we should play. And what we need to do is the same way as we just looked at the Wampus world, where we define sort of information about the game itself, where we said, okay, what does it mean for something to be breezy? Namely, if there is a sensoric information that there is a breeze. We have the notion of adjacency, so the two fields are adjacent. And this is not yet a specific game that we model, which would say, okay, my agent is in this situation in position 1.3, and in 1.4 there is a pit. That's the sort of the game-specific information, but we want to particular also model information about the strategies of the game and the situation of the game in general. So, for example, we can use specific game information that the King of Hearts is high given this specific situation. So that is a qualitative bit of information that we derive from the state that we are in. So that is using a game specific, but it also really is, that's a definition of the state in which we are in as players. But then there's also the generic knowledge, namely that the ace of spade is an expensive card, because it always is in any game, it gives you 11 points. So it's independent on the state that we are in. And this is information that we can use. So there's different levels of information about the games that we can model. And some of it is sort of just a technical thing, which we don't have to look into that much. But the good thing is that we can now make our heuristics very explicit and also to be discussed. It allows us to discuss the different strategies between humans, between the users, between the developers of the game. Yeah, so the idea is here, let's make these strategies not only help us with dealing with all this uncertainty, but also make it explicit and declarative so that we can discuss it with people and then we can reason even over the strategies. So the decision-making works as follows. We represent the necessary knowledge in a suitable formalism. And we do that for the environment knowledge and the knowledge about the state. And then we represent this knowledge that we have modeled as a decision problem in our specific logic. And then this becomes an entailment problem to which we can apply an automatic reasoner, so the calculus, of which I'm going to talk about tomorrow. And the outcome of this, this reasoning process will give us the answer of what is the next move to take. Now the question is, sort of, as you have noticed, I maneuver a little bit between the two formalisms of propositional logic and first-order logic. And that is, makes things a bit more complicated on one way, but has some formal reasons, and I want to get into those formal reasons in a minute. But be aware of the fact that I model sometimes in propositional logic, sometimes in first-order logic. And that's I think one of the classical, is a really nice example for the classical problem of knowledge representation, where you want to find the optimal language for the specific task that you're dealing with. And my understanding of the problem here was that modeling in first-order logic is the best thing to do, but reasoning in propositional logic, surely given the specific properties that we're here in a sort of introductory AI course, it makes sense to deal with automatic reasoning and propositional logic. This is sort of a meta argument. The other one is that there are also theoretical properties that invite people to use propositional logic for reasoning. And those are, first of all, that first-order logic has very bad computational properties, a thing I will talk about in a minute. And the second one is that we have finite domains and very small domains to talk about in our examples. And that basically means that we are dealing in Schnapsen, we're dealing with 20 cards. So all we do, whenever we quantify over objects in the domain, it is always a domain that has maximally 20 objects in the domain. So we have a relatively restricted set of rewrites to do. But let me do a bit of theory of computation. But that is in principle what you have to be very aware of, that I use two logical formalisms for two different purposes. I use first-order logic for representation of the knowledge, and I use propositional logic for reasoning. And there is an intermediate translation step, which is a little bit tedious and not so well worked out. So we'll see that later. But there are good reasons for doing that. And part of it, excuse me, I have to drink. Okay. Who knows who this person is? Okay. Did you in the back hear what was said in the front? Do you know who this person is? No idea? That would be an interesting experiment to check whether there is a correlation between the rows numbers and the knowledge about computational theory. So this is Alan Turing, my hero, and I have a little bit the tradition now in the past 10 years of giving lectures that I always have one lecture of sort of devoting one slide to Alan Turing. Because I think he has been, in the past century, he's been one of the heroes of our field in so many different respects that it's one should devote a whole lecture to him. Alan Turing not only invented not the field, of course, but at least the name of artificial intelligence. He wrote first papers, and he also was the first to come up with an operationalization of what does AI mean in the first place by his famous Turing test. So in a way that is almost philosophical, his contribution of what does AI, what does artificial intelligence mean in the first place. And his definition was if we have somewhere a communication challenge, a communication with the machine and the human in two different rooms, and we don't know who is the machine and who is the computer. And if the computer can make us believe that it is the human, then it has passed the Turing test. And we can ask any question and communicate with this thing where we don't know whether it's the human or the machine. And there have been many people criticizing this, and there have been there are many shortcomings to this idea. But this was an idea that came up in the 50s, I believe, of the last century. And it was really valuable in terms of operationalizing what AI research is supposed to do and can achieve, and how that we also need to make it measurable what it is. So that was one contribution. So it really is sort of setting up a field, helping us define what we want to achieve. More importantly for me as a mathematician is this work. So it is the work that he did 20 years before, his AI work before the war. And that's basically the work on showing that there are things that we cannot compute. So things where we know in principle whether some information is true or false according to the knowledge that we have. But he showed that there are problems where we can never give an algorithm that generally solve these problems. This was a result that was given before we even built the first computer, and it was an incredibly deep result. And I'll get back to that in a minute. The third thing was his practical work, his practical contribution to winning the war against Germany, of course. So he was one of the, if not the most instrumental person to help crack the German codes during the war by mathematics, but more or less, because he came up, combining mathematics and engineering, I would say, because he came up with methods to crack this Enigma machine, given some partial information and then some expensive calculation. And I think through his contribution and his colleagues, of course, at the Fletcher Park, is one of the reasons why the war ended earlier than it did and saved a lot of lives. So he really had an incredible contribution to history of the last century. And the last thing is that he was basically driven into death, into suicide, as most people expect now, because society didn't accept the way he lived, the way so his homosexuality was not accepted at the time, and he was basically banned from teaching. He was treated, as it was called at the time, and it was the inhumanity of our society at that time that brought one of the most brilliant minds and most important minds of the last century to bring himself to kill himself. So on the one hand, he is an incredibly fantastic figure in computer science, in history of the 20th century, and he's also sort of, to me, he's always the example that we should be tolerant, not only because he was a genius, we should be tolerant to everybody, of course, but I think it's always good to mention that this was part of the history of Alan Turing. So I don't want to stop here because it would be a bit depressing. So I want to go on for 2 more minutes and talk about the thing I really liked, is the most important for me. And technically speaking, and this is mathematical results. And basically the question at the time was, suppose we have a formal system for which we can have some notion of a knowledge-based entailed formula, and we define that properly. So there's an ambiguous notion, can this formula be derived, is this formula entailed according to the model theory? And then the question is, do we have a decision procedure? Can we write an algorithm that tells us, and I abbreviate the algorithm with this symbol, is there an algorithm that tells us whether the formula is entailed or not by some calculation, by some algorithmic solution? So basically the question is, can we always automatically give an answer, given some algorithm, to the question whether something is true or not, given some knowledge base, and so forth. And Alan Turing showed that this is not the case. So that there are examples for which we cannot write a generic algorithm that will always give us an answer whether this is true or not. Yeah?
What was that called? What's the name of that theory?
The halting problem. Yeah? And I will talk about the halting problem after the break. So let's please come back at 12 o'clock it is. Okay.